Nick. Could you give them that? Could you give Ray a thumb?
Nee, dat is John Kill.
Well, it's
Gigi Kill wilde dit. John Kill is de man
was the lower.
John Kill.
John
Gigi Kill is meer zo'n country sneetje bloem.
Ik ken de naam van Gigi Kill.
Oh, no. Oh, yeah, gitaar van ik Mark Knopfler.
We all here?
Yes, I should.
Okay. Okay, so, well, as ever, to start, before I forget, I want to thank George for inviting me, for all his great hospitality, which is fantastic. It's a great place to come. And I should also say, I don't know whether, this is probably not maybe true of everyone, but it's certainly true of me. I mean, having the opportunity to talk, at meetings like this, where we have, Basil's been kind and given us nice lots of time to speak. I mean, this is a kind of great motivation to actually do the work, so having the opportunity to speak is actually helps one, forces one, I suppose, to think hard about what one is trying to do. So, just to say, like some of the other people here, like Nick, I sort of see a bit of parallelism there, because I started off I was actually a PhD student of Dennis Sharma in Oxford in the 1970s doing classical general relativity. I went through sort of agonies in the last year trying to decide whether to carry on with the subject. I had a postdoc opportunity at Damped with Stephen Hawking, which would have kind of got me involved in quantum GR, and I couldn't get my head around quantum mechanics at all, despite I did all the courses and stuff. So that was kind of partly influential in deciding to change field to something more, let's say, societally useful. So I've been, the last 25 years or so, I've been doing weather and climate research. And in fact, Basil asked me, if there's time, he said, I've got a kind of public talk I give on global warming, and I could maybe give some of that later on if you're interested. So that's what I've been doing. But it's a bit like a Jesuit education, I think. If you do sort of fundamental physics, it never quite, you can't actually quite shake it off, hard as you try. The sort of stuff about what does quantum mechanics mean in the context of gravity and so on is sort of has been dogging me. And I suppose what I'm going to try and bring to the table is some perspectives which sort of have been brought from my own more professional work on nonlinear dynamics applied to the atmosphere. After all, chaos theory, in a sense, modern chaos theory arose from actually a good colleague and friend of mine, Ed Lorentz. This is L-O-R, this is Lorentz without the T. Who actually, derived one of the prototype chaos models by trying to understand the unpredictability of weather. And of course the great achievement he made was to show that this unpredictability could be explained with a very low order dynamical system. So what I want to try to, as I say, bring to the table some ideas from that sort of subject matter. So Basil's kindly sort of scheduled 2 talks for me, and I think his intention or hope was I would talk a bit about global warming in the first talk, and then talk about this more quantum stuff in the second talk. What I actually want to do is the following, if it's acceptable. So George, for example, sent round an email asking us to, not perhaps launch into all the technicalities right at the beginning, but say something about the motivation and the basic idea. So what I thought I'd do is maybe spend, hopefully, 20 minutes or something, just talking about the motivation for what I want to talk about. And I won't talk about any kind of mathematics as such. I don't think there's any equations in these first few slides. So I'll maybe get to the point, where the maths might start, and then leave that for tomorrow. And then, if there's still interest, I'll talk about climate change. People are asking about climate change. So, but I wanted to, because I don't want to kind of run out of time tomorrow, and I don't want you to get, you'll start, I think, to lose concentration if I just do an hour and a half of this stuff. So let me kind of break it up. So I'll just spend 20 minutes trying to describe. This is my hobby, if you like, which I entitled the mysteries, plural, of entanglement, and that's come from basically a quote. So the first two slides are just quotes, and the first, so the two mysteries are taken from Roger Penrose's recent megatome. I'm sure some of you have seen it. I still find it curious that almost everything is in this book, except perhaps the most important stuff he did, which is the singularity theorems. There's nothing about the singularity theorems in this book, so that's an interesting psychological question. Why did he not discuss that? But anyway,
I will ask him next.
Yes, I think it's because it's established. It's uncontroversial physics.
Oh,
everybody agrees with it.
He only wants exciting stuff.
Yeah. Anyway, so here's the quote. It seems to me there are two quite distinct mysteries presented by quantum entanglement. So number one is the one that he says everybody is aware of, and this is something that's perplexed us from the moment entanglement was discovered. I'll show you there. How are we to, and EPR and Bohm and so on, and crystallise the mystery? And how do we make sense of this idea of non-locality, essentially, in terms of ideas that we can comprehend? But then he also poses this one, which he says is something which people don't tend to ask. But if you take Schrödinger evolution seriously, then all the time, as the world, the universe evolves, things are just getting more and more entangled. Everything's getting entangled with everything else, and it's becoming a kind of a horrible clutter of entanglement, and it goes on and on, it increases. But yet, why do we kind of seem not to really notice in our direct macroscopic experience of the world this kind of ever-increasing entanglement? So this is his second mystery. And I want to present, let's say, proposals to both of these two, and in a sense they're both related. They are proposals. They're not by any sense of the word mainstream proposals, but this isn't my job. So in a sense, my career doesn't depend on it. So in some sense, I don't really care if it's crazy or not. So the first point is to make the claim, and I try to give some justification for this claim, that we will be able to understand quantum entanglement conceptually if, or as and when, let's say, quantum theory can be recast and embedded in a nonlinear deterministic theory of some larger type. Now, the particular type I want to talk about are ones where there are very strong dynamical restrictions on, let's say, dynamically allowable states. And in particular, the restriction is to a very small dimensional subset of state space. So this will become more, I think, obvious when I'm talking about very shortly. Now, the second point, which is definitely, I think, more controversial, is that on the basis that, as and when we can do this, then I think we will find that we do indeed notice entanglement in our direct experience of the world, and we already call it something. We call it gravity. So I am proposing that gravity is not some sort of extra force that we quantize along with electromagnetism and weak and strong interactions and so on. It's actually a basic property of quantum theory, but not quantum theory as we understand it now, but quantum theory as we will understand it, hopefully in a sense which will make entanglement more understandable conceptually. So in some sense I do see this proposal as a little bit like, when we go from Newtonian physics, where gravity is a force, into GR, where gravity is not anymore a force, it's just a property of the state vector, in other words, a metric, it's the curvature. So in this framework, gravity is no more a kind of part of the Schrödinger Hamiltonian or something like that. It's just a property of the state vector, the entanglement. So that's the claim.